Okay, so until so far in this course we have been focusing about the size of a polymer chain, and we discussed two different measures, the end-to-end distance and the gyration radius, and we did for various cases accounting for the interactions between the segments. First we looked at the ideal chain where there was no interactions. Then we did the case for a self-avoiding walk when there were repulsive interactions or repulsion between segments. And then finally we did for the bad solvent case when there was attractive interaction between segments. But we have focused only on the end-to-end distance or the gyration radius or the distribution of the same quantity as a function of the number of segments. So now I want to talk about some things different that we care about in a polymer chain, and that is the shape of a polymer chain and the structure of the polymer chain. Okay. So in general, while the size tells you about how large or long something is, let us say a sphere can be small, larger, even larger. This is what is captured by the size. The shape tells you what does it look like. So objects that are having the same size may have different shapes. For example, a circle, a triangle and a square may have similar characteristic dimensions, but they still have different shapes and they look differently. And then finally comes the point of structure, which is tells you how ordered or disordered the system is, and we will take this point, the order disorder, later on. Let us first talk about shape, okay, and why it hasn't come into discussion so far and how can we include that and so on. Okay, so far we have not differentiated between the different directions. They are assumed to be identical. For example, if I am computing the Rg square, of course I can compute the three components Rgx, Rgy and Rgz square, and we have done that at least for the lattice case, just to demonstrate that I can decompose a walk in 3 dimensions into 3 one-dimensional random walks, and I can get the Rgx, Rgy, Rgz for each of them. But if I take an ensemble average of all of them, squared of them, they have to be equal, and in fact should be equal to the squared of the Rg in total divided by 3, because we know that Rg square is Rgx square plus Rgy square plus Rgz square. So this particular assumption assumes the chain to be somewhat isotropic, that is, there is no difference in the different dimensions, or does not matter how I look at the chain, in every direction it will look out to be identical. If I do an ensemble average, of course in a particular conformation Rgx can be higher than Rgy, Rgy can be higher than Rgz, but if I take an ensemble average over many conformations, the squared average in ensemble sense will be the same in all the 3 directions. That need not be the case always. For example, if we have a rod that can be an approximation for example, a stiff chain, then in that case it is clearly more elongated in one direction compared to others, and this must be taken care of when we are doing the analysis. However, if you look at from fixed reference frame, let us say if I fix my reference frame here and I look at a polymer chain that is stiff or like a rod, then of course this chain can be taking different orientations. And again, if I think in terms of the average values, they have to be the same, because it is equally likely that the chain is elongated along the x direction and the chain is elongated along the y direction and along the z direction. In fact, at any angle in the three-dimensional plane, the probability to have the chain axis is identical. Okay. So, if I look at from a fixed coordinate frame, we cannot capture the effect of elongation. Okay. So, the way of doing this, way of capturing the effect of elongation, is we fix our frame of reference to the polymer chain itself. That is to say that let us say if this is my polymer chain, I will fix my reference frame. Let us say I can set the center of mass as my origin, and then I can set my frame along the chain axis. Let us call this 1, 2 and 3, and what I also do is to ensure that my R G along 1 axis 1 is higher than equal to R G along 2 higher than equal to R G along 3. If I am doing this in this particular way, 1, 2, 3 are referred as the principal axis, and then the principal axis are also named like major and minor axis, and then this coordinate frame will move as the chain takes different orientation. So, 1 is always along the most elongated dimension. So, in that sense, if I take an ensemble average, the ensemble average of R G 1 square must be higher than equal to R G 2 square must be higher than equal to ensemble average of R G 3 square. Okay. So, this is one point, that we must fix our frame of reference should be fixed to the polymer chain. However, there can be other cases where there can be elongation also along the fixed reference frame. For example, if you imagine a confined polymer chain, so let us say you have a cylinder through which a polymer chain is passing, and now since the way we have drawn, the diameter is either comparable to or lesser than the radius of gyration, or it can even be of the same order, and the effects will start to appear. So, if the chain dimensions become comparable to say the diameter, in that case the chain has to elongate in the other direction, because the chain cannot cross the cylinder, so it has to get elongated in the other direction because of the confinement. Okay. So, in this case if I fix my axis, I will see that along the x the chain will be more elongated, and along the y and z they have to be less elongated. Okay. So, for a confined polymer chain we can work with fixed reference frame, and for a stiff chain the reference frame should be fixed to the polymer. Okay. Actually, also for the confined polymer chain we can fix the reference frame to the polymer. That will not make an error, but it will not capture the effect of confinement in true sense. Okay. Now, let us see how does these Rg values along the principal axis relate to the definitions of Rg that we have discussed earlier. And it turns out that we can define a general tensor called the gyration tensor, which basically captures the anisotropy or the fact that the chains can be elongated in one dimension more than the other dimension. Okay. So, one can define a gyration tensor and this can be defined both for the frame of reference fixed to the polymer chain or for the fixed reference frame. So, we can define a gyration tensor as some tensor S which have components alpha beta given as 1 by m sum over I equal to 1 to m. So, when I was doing the Rg squared, I took a square of Ri minus Rcm. Instead of that, I will do Ri alpha minus Rcm alpha, we are following the Einstein notation, and Ri beta minus Rcm beta, where alpha beta for 3-dimensional case are along the 1, 2, 3 or x, y, z, depending on how are we defining it. Okay. So, now this is in Einstein notation. Now, irrespective of like what reference frame I started with, if I look at this particular matrix and I compute the eigenvalues, it always gives me the eigenvalues always gives me the Rg along the principal axis of deformation. Okay. So, these can be thought of as eigenvalues. Actually, we will look at the squares of these quantities for the simple reason that the gyration radius, gyration matrix is squared in distances. So, the eigenvalues will come by diagonalization of S, that is the standard stuff that we do in any eigenvalue problem. So, essentially the way we do it is we look at determinant of S minus lambda I is equal to 0, where I is my identity matrix with ones along diagonals and 0 everywhere else, and lambda becomes my eigenvalue, and once I solve I will get 3 solutions for lambda, which gives me Rg1 square, Rg2 square, Rg3 square. If I look at the eigenvectors, they will give me the principal axis of deformation. So, this becomes, let us say if I start from XYZ frame as the reference, so we have to solve this particular relation that happens to be a cubic equation in lambda, and this gives me the 3 eigenvalues. So, now if I want to represent my anisotropy or asphericity, because if the eigenvalues are identical, that is what we assume for random walk, we are assuming that the shape is akin to a sphere. Okay. So, if we represent my anisotropy or asphericity in terms of departure from the sphere or isotropic behavior, we can look at the ratio of these eigenvalues which can be my measures of anisotropy or sphericity. However, there are better measures and I will come to that. What we can also see is I can look at different shapes and see like how exactly their Rg1, Rg2, Rg3 varies, and see like how then we can look at these Rg values and tell about what the shape looks like. So, for example, for the case of a sphere, let me draw it like a sphere with a constant radius. We have Rg1 square so all three are the same as we discussed. If it is however an ellipsoid, now there are actually three possibilities. One is that we have Rg1 square comparable to Rg2 square, which however is higher than Rg3 square. So, two of them are more or less similar and the third one is smaller, that is called an oblate ellipsoid. If on the other hand we have one of them larger and other two comparable in shape, we have what is known as the prolate ellipsoid. If however we have all three different we have a general ellipsoid. Okay, that is one point. And so we can look at these values and that will tell me like how the shape looks like, right. So, in the extreme, let us say if we have a rod, in that case Rg1 square is very high and Rg2 square and Rg3 square have to be very small, because they refer to the thickness of the rod, that is anyway very small, especially compared to the length of the rod. Okay. So, what this tells me is these eigenvalues contain a measure of the shape, and we can characterize the anisotropy using these eigenvalues. Okay. However, the ratios that we have defined as the measures of anisotropy and asphericity are not the best ones out there, for the simple reason that these ratios take values going from say 0 to infinity. So, it is better to have measures that vary from say 0 to 1, where 0 and 1 refer to two extremes. So, in that sense it will be more convenient than compared to the measures we have, because this can take a very large value or very small values. Okay. So, we will look at this particular characteristic equation we have derived, that is determinant of the gyration tensor minus lambda I is equal to 0, and based on that, apart from this Rg1, Rg2, Rg3, which are the eigenvalues, actually squares of them, Rg1 square, Rg2 square, Rg3 square, which are the eigenvalues, we can also define something known as matrix invariants. What essentially they mean is those invariants will be independent of the rotation or translation of axis. Okay. If for example, I have defined this invariant for a particular reference frame and I rotate my axis, those quantities will not change, and that is what is known as invariant. The same thing will be true if I translate my axis somewhere. Of course, the matrix overall will be different, but those invariants will remain unchanged. Okay. So, it turns out that the characteristic equation that I just showed you contains 3 matrix invariants which are, first of one is my trace, that is defined as Rg1 square plus Rg2 square plus Rg3 square. The second one is the product of them, and the third one is Rg1 square, Rg2 square plus Rg2 square, Rg3 square plus Rg3 square, Rg1 square. And using these 3 invariants, actually only 2 of them, I can define a measure known as asphericity as trace square minus 3m divided by trace square. Okay. So, before we go into what this A means, let us first derive what the trace square minus 3m is, and then see what the expression of A is actually. So, trace square minus 3m will be Rg1 square plus Rg2 square plus Rg3 square, that is the trace, squared minus 3 multiplied by Rg1 square, Rgt square plus Rg2 square, Rg3 square plus Rg3 square, Rg1 square. So, now I can expand the first one and I get Rg1 4 plus Rg2 4 plus Rg3 4, and then we get 2 times, actually I will get the entire thing that we have here, and then we have minus of 3 of the same quantity, and so we can write okay. So, bit of a manipulation here. So, what we do here is I write this as 1 by 2, and then we have twice 2 coming here. So, we have 2 Rg1 4 plus 2 Rg2 4 plus 2 Rg3 4 minus 2 Rg1 square Rg2 square minus 2 sorry, it has to be Rg1 here. And now I can form squares. And what this gives me is 1 by 2 of Rg1 square minus Rg2 square whole squared plus Rg2 square minus Rg3 square whole square plus Rg3 square minus Rg1 square whole square. Okay. And this I can now write as trace square minus 3m is equal to one by 2 sum over I greater than j Rgi square minus Rgj square whole squared, okay, where I, j vary from 1, 2 and 3. And we know what the trace squared is. Trace squared is simply summation of I Rgi squared whole squared, and so our A become equal to one by 2 this, and of course there has to be an ensemble average coming here. Okay, so we can generalize it for a d dimension. So essentially I can replace 2 by d minus 1 for d dimension, and we can show that this indeed works out. And now we can see like how exactly it is a good measure. So, let us say what happens when we look at a sphere, in which case Rg values are identical. So, the numerator will always be equal to 0, because if I square and take a difference we get 0. So, A equal to 0 for a perfect square, perfect sphere. On the other hand, if I have a rod, then Rg1 of course is equal to the length, but Rg2 and Rg3 are pretty much comparable to 0. And so, what I do get from this is A is equal to 1 by 2, and on 2 occasions Rg1 square will appear, everything else is 0. So, we have 2 Rg1 square, actually square root of that. So, 2 Rg1 4, and then divided by only one occasion Rg1 will appear, and that is squared. So, this is equal to 1. Okay. Keep in mind that we are assuming a perfect sphere and a perfect rod. So, ensemble average does not have any meaning here. The key point here is we are going from 0 to 1 here. The higher the value is, the more anisotropic or aspherical it is, and the maximum possible value is 1. So, in this way this particular quantity A characterize the shape of the random walk or all kinds of walk that we have done. Such as the self-avoiding walk. Okay. So, we have now covered how to characterize the shape of a polymer chain. Earlier we have looked at the size of the polymer chain. So, in the next lecture we start talking about the structure of the polymer chain or a polymeric system. Before we go into it, we will discuss about what do we mean by the structure. We talk about order and disorder transitions, and we take a detour to talk about the scattering theory, and then we will return to the idea of structure of a polymer chain or a polymeric system. So, with that I stop here, and then thank you.